So I've got my sheet just like you do. There's mine. And we're going to look at three kind of special cases of one-dimensional motion. So we're graphing one-dimensional motion. In the old AP physics, the one that we threw away like 5 years ago or now or something like that, we did almost no graphing. And in the new AP physics, they really like graphing, which is why we need to spend some good time on this. So we're going to draw some different situations here and fill them in and see how we do. So in each of these cases, we're going to start with a displacement versus time graph. I'm going to give you the displacement versus time graph, and then we're going to build the velocity versus time graph and the acceleration versus time graph from it. Okay. All right. So the very first one that we're going to do is pretty unexciting. Nope, not that. That's really unexciting. Let's do this. That's a little more exciting. Tell me the story here. What is the story of my frog, let's say? The story of my frog, if this is his displacement versus time graph. What's he doing? He's chilling, right? Yeah, he's not moving. I'm just going to make a little note here that the object is not moving. Now, you told me just a minute ago when we were looking at that other problem that was much more difficult than this one, you told me that the way that you find a velocity versus time graph or the velocity values at any point are to look at the what from this graph, from the displacement graph? The slope, right? So the slope of a d versus t graph are going to tell you the values of the velocity versus time graph. And in this case, the slope is what? 0. Come on, silly. This is not a good day for this to happen. Come on. Okay. If the slope of this is 0, that means the values for the velocity versus time graph are going to be 0. Talk about an unexciting graph. Whew. Pretty boring. Okay. If the velocity is 0 the entire time, is the object accelerating, ladies and gentlemen? No. So we can draw that acceleration versus time graph. That's pretty darn easy. And the tricksy calculus that we're doing there is that we're looking at the slope of this, right? Slope of this is 0. So that means the values here are going to be 0. So we're going to write it down. The slope of a velocity versus time graph are the values for an acceleration versus time graph. But let's be honest, that's a pretty unexciting story. Right? Like, great, that's awesome. Thanks for that. All right, let's do this one. Let's make a new story, something that's more fun. Displacement versus time graph. What's it doing? What's it doing, Razan? Moving at a constant speed. Yay! That's fun, I guess. You know. We're going to look at the slope of D. Say that again. Absolutely, it does. That's an awesome question. Does displacement include direction? Absolutely, it does. Displacement, velocity, and acceleration are all what we call vectors, right? So they have direction and magnitude. Yes, yes. What's the velocity versus time graph going to look like now?
It's going to be a horizontal line above.
Indeed. Pretty exciting. Woo, 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 woo. We're going to make an observation here just to kind of help us understand this. The values here are constant and positive. Oh, by the way, the slope here was constant and positive. What's the slope of this one? 0. So that means that the values here will be what? 0. Yeah. How are we doing? We okay? Okay. So to go this way, we're always looking at slope. We're looking at slope. We're looking at slope and slope and slope. Let's make it even more exciting. More exciting. Here it comes. Pretty exciting, right? Tell me about the slope here. It's increasing, isn't it? And not only is it increasing, but it's increasing and it's always what? Positive. And if the slope here is increasing and positive, what are the values here going to be? Hey, hey, look at that. Increasing and positive. Cha-ching. Tell me about the slope here. It's constant. Constant and what? Positive. And if that's a constant positive slope, what are the values going to be over here? Yeah. The concept here is not super difficult. And as I said, given that we have kind of a range of mathematical experiences in here, for some of you this is like, yeah, I got it. For some of you this might be the first time or the second time you've seen this. So I'm hoping that this is helpful. Okay? It's also going to provide us a couple of opportunities just to make sure that we really understand where these things are coming from. If I have a change in D over a change in T, that's the slope of my line, right? And the slope of my line, change in D, or change in position, over the change in T, is really what? What is change in position over time? I heard somebody say it. They whispered it.
It's Henry.
What'd you say, Henry? Or somebody. I don't care who. Just tell me. What's the change in velocity or change in position over time? It's velocity, right? Yeah. This is why that's true. Can we extrapolate over here as well? Change in velocity over time. The slope, the change in the velocity over time, is equal to the what, guys? Indeed. Okay. This is why all that calculus business works, right? This set of rules empowers you completely if you're given a displacement versus time graph to figure out the velocity versus time graph and the acceleration versus time graph. You now know everything you need to know to go from one to the other. Okay? Moving to the right on this chart. We want to move to the left as well. You can flip this over on the back if you want to write this down. I don't have a fancy little sheet for you on the back, but we'll talk about it here quick. Okay? You can also move back to the left, and I just want to make sure that you understand this because it's important too. Oops. Zoom in a little bit here. So I'm going to draw a displacement, velocity, and we'll do acceleration later. I guess we can do it. Let's say that I know that my velocity versus time graph looks like this. And just for kicks, let's say that the velocity is 3 meters per second. And let's say just for kicks that this thing lasts for 2 seconds. Okay, just trying to give some context to this. It's a pretty straightforward question, ladies and gentlemen, but let me just ask it. If you're moving at 3 meters per second for 2 seconds, how far do you go? 6 meters, right? You're like, duh, I did that on the first day of school. I got that. First day of first grade, I got that. No problem. But here's the fun part, ladies and gentlemen, if you've not seen this before, that, oh my gosh, you've just got a nice little rectangle, don't you? And the area of that rectangle is how much? 6. Oh, it's kind of cool that you've got 3 meters per second times 2 seconds, and hey, that gives you 6 meters because you've got an area of 6. So I know that in those 2 seconds, 2 seconds, I know that my that my object has moved 6 meters. So I started off at 0 and I moved up to 6. Okay? So the area, 2, 3, 4, 5, 6. I know that if I start at 0, by 2 seconds, I've got to be way up here. Holy cow. Something like this. Okay? Look at that. Constant positive slope. Constant positive values, area of 6, displacement of 6. You with me there? Now, if Harrison were here, I'm channeling my inner Harrison for you, okay? He would say, well, Miss Carmeling, you don't know where it started. And I would say, you're exactly right, Harrison, that's true. Because this may have started down at -4, right? We don't know that. That's the initial condition business. We don't really care about that right now. But then it would go up to +2, okay? But we know that the displacement is 6 meters. So now I've got my displacement graph, I've got my velocity graph. What's the acceleration graph going to look like at this point? 0. It's not very exciting. All right. Let's do one more. Or maybe 2. We'll see. Okay. Displacement versus time, velocity versus time, acceleration versus time. How about this one? And let's say that goes up to, 10. How did we find our displacement in the last one? What did we look at on the graph of our velocity graph to find our displacement? The area, right? The area of the rectangle. So here's the question. Here's the question that I would pose to you. I've got an object that starts off at 0 meters per second. It gets all the way up to 10 meters per second. Takes 3 seconds to do that. How far did it go? Where are you getting that from, Jasmine?
Because you said it was, the first one was the area,
Uh-huh.
distance of that graph.
Yeah.
That's a triangle. height is 10 and the base is 3 inches.
You got it. Yeah, we got a nice little triangle here. Can you find the area of a triangle? Why, yes, you can. All of you have done this. No matter what math you're in, I know you've done this part. So the area of this triangle is 1/2 base times height, right? Awesome. The base is 3. You got 10. 3 times 10 divided by 2 is 15 meters. You got it. So I know that in those 3 seconds, my object has moved 15 meters. Okay? How did it get to 15 meters? You know? Here the values are constant, are increasing and positive. So here the what needs to be increasing and positive? Slope. So it's going to zoop, parabola up. Yeah, look at us doing some calculus today. It's beautiful. And in those 3 seconds, we get all the way up to 15 meters. Okay. Slope gets bigger and bigger and bigger and bigger and positive. What's the area or the acceleration versus time graph going to look like? Straight line. What kind of straight line? There are lots of different kinds of straight lines. A slope of 0, it's true, and a value of something. I mean, you could do the math. How are we doing? We okay-ish? So the moral of the story here, ladies and gentlemen, is that if you move to the right on graphs, if you set them up this way, DVA, you move to the right, you're going to look at the slope. Slope determines values. If you move to the left, the area determines the values. Okay? Now you've learned all of first and second semester calc. You're welcome. All right. What's that? I mean, well, yeah, this is the principle behind it, right? All right, I'm going to give you a few problems to work on because I think that's good for your brain and make sure it makes sense to you. I'm going to come around and answer questions if you have questions. And then there are a couple of problems for homework, and I'll put those back up so you can write those down as well. But you got, a few minutes, right? We've got a few minutes to get started on this. What did you say, Baker?
I really hope I do.
Oh, yeah. It's not the cheap stuff. All right, ladies and gentlemen, get started. Give it a shot.